All right, hello there. I'd like to take the opportunity to make this video right now, which will explore what cool things you can get from a vector field, even just defined on the plane, which is curl-free and which also exhibits some sort of singularities. So there's a lot that you're seeing on the screen right now, and on the top in the black box, I've described a vector field. It's got two components, a p and a q. P, oops. It's got a p and a q, and each is a function of x and y. Okay, and you see a lot of stuff in the denominator. So denominator is always going to suggest to you, uh-oh, you might be dividing by 0 somewhere. And I've actually, algebraically split up the vector field, which you're allowed to do. Remember, a vector field is a vector at every point, and we certainly know how to add and rescale vectors at this point. So all I've really done is I've factored and done some fancy algebra to move stuff around. And it might be helpful to look at the vector field V as a decomposition into V1 plus V2. So it's a mess right now, and I don't expect anybody to have any sort of intuition for what the heck is written in that top box up there. It's a lot of stuff going on. And I spent quite a bit of time just trying to I tried to get certain properties of a vector field to pop out, and I got the above equations to sort of fall out of what I wanted to get. So really, we can decompose V into V1 and V2. And you see that we do have some denominator going on. We have some potential of dividing by 0. So you see that we have division by 0 in the V1 component. So here's a vector, which is rescaled by a function. It's a scalar. And again, in V2, we have a vector field, which is rescaled by a function. Okay, and the whole top thing is V1, and the whole bottom thing is V2. So you'll notice that we have a singularity of V1 at 1, 0. You just try to figure out what numbers can I plug in, which will make that denominator equal to 0. So I'll highlight that. This is 0 right here. And similarly, this is 0 right here. So my total vector field is defined, my total vector field in this box right here, which is the same thing as up here. I just did a little factorization. This whole vector field is defined everywhere except at these 2 points. I can't plug in those 2 pairs into my total vector field. Okay. So we could spend a lot of time figuring out what the vector field looks like. I can plot it at any point that isn't the yellow or the blue. We can figure out, what it starts to do, but I thought let's just skip that time and let me just make GeoGebra plot it for me. So over here, I've actually plotted what the vector field looks like. So here was that singular spot, and here was that other singular spot. So you're noticing like a double rotation. The integral curves or the flow lines kind of like to move around these 2 spots. Okay. So there's a lot going on in this picture, but I'll actually take away the thing I just drew. You see there's sort of singular spots and rotation around those singular spots. And what is happening to the vectors along the vertical x equals 0 axis, the y-axis, all my vectors are pointing due south, down, 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 down. So I was going to spend some time figuring out what the vectors do at different spots by plugging in different points and plugging into the vector equations, but I figured let's just look at the picture itself. All right. So we've had lots of experience with vector fields with singularities. We made a whole video series about, oops, oh no, okay, that's a lot. Okay. Oh no, how am I going to get more pages? It's okay. Okay, that's how I add pages. I'm sorry, I'm learning how this all works. Okay. All right, cool. That's how we'll add pages. Okay, so we've had experience with vector fields that have singularities that exhibit some rotation. I mean, our quintessential example, which we've spent tons of time working with, is negative y over x squared plus y squared, comma x over x squared plus y squared. We know that this vector field is a counterclockwise rotation about the origin. And the craziest thing is that although it's swirling around, it does exhibit zero curl. So this thing is curl free. Now, the idea is that the vector field over here is kind of two modified versions of this vector field that we've spent so much time studying. Curl free with singularity about the origin. Recall that we made I made a YouTube video which says V is is roughly the gradient of the angle function. V is basically the gradient. This is the gradient. And theta is the angle function. The sad part is that the angle function isn't a continuous function defined on the entire plane. There's always a strip on which the angle wants to be both 0 and 2 pi. So that's kind of the issue. The issue is that this is not a continuous function, but V is a continuous vector field. So there's something that's going on there. And that's really what we're going to explore more today, but just times 2. because we've got 2 singularities, and we kind of have 2 angles that we're measuring. So in the spirit of what I just said, I claim that this vector field up here that I've written, this super big mess that has a double singularity, a yellow and blue singularity, I claim that this thing is also curl free. So you can compute the curl of this vector field anywhere that is not the yellow point or the blue point. And I've actually done this. So I'm going to move the page, and I've done this right here. The computation it's kind of messy. It's not too enlightening, but you can actually compute that the curl of V, where V is that thing on the previous page, the thing with the double singularity, if you work it all out, it turns out to be 0. Okay. The idea is that this vector field V is kind of a sum of 2 shifted versions of of that single rotational vector field that I drew. So I don't think this algebra is terribly enlightening, but it does work out. This vector field is curl free. The curl is 0, that's for sure. But I want to kind of tell you how I came about this formula up here. Like, why does this vector field actually work? And I think there's a more intuitive explanation for why it is curl free, for why these numbers work out to give you 0 at the end of the day. So I want to tell you the process that I took before I did all of this. So before I even found the expression for V, I knew what I wanted was in the XY plane. I wanted to somehow develop a function. So these were these 2 special points. I did have those 2 special points in my head prior to setting all this up. I wanted to somehow, at a point x, y, I wanted to measure the angle that I saw here. So I called this angle theta 1, and I wanted the angle measured from this side to be theta 2. I wanted f of x, y to roughly be theta 1 plus theta 2. At the end of the day, I knew that the gradient would define something that's curl free, that's not defined at these spots, and which exhibited some rotation about the yellow and the blue point. So I knew once I could find the formula for f, then the gradient would be a really cool vector field that we could learn a lot from. So if you just start plugging stuff in, if this point is x, this length is 1, then this triangle has height rise over run y over x minus 1. And so theta 1 looks like the tangent of y over x minus 1. Then I wanted to know a formula for theta 2, which was this angle here. So to get a formula for that, I really looked at, I made an auxiliary function phi, and I said theta 2 plus phi is pi. Where I got this thing from is just looking at this full angle as a full theta, and sorry, is a full pi. And I know I could get a pretty nice formula for phi using the same equation. So I'll highlight it in green right here. And this is the big triangle that I look at. And I could say that phi, oops, sorry, everybody. This should be arctan of y over x minus 1. Similarly, phi should be the arctan of rise over run, and my rise is y, and my run is x plus 1. This tells me that theta 2 is pi minus arctan of y over x plus 1. So the function that I was thinking about, that I was creating in my brain prior to prior to all this work, the function of xy is really something like arctan y over x minus 1 plus pi minus arctan of y over x plus 1. This function takes a point and it spits out a sum of two angles, this angle and this angle. And I'm not going to do it for you because it's a mess, but I promise you, if you compute the gradient of this function, you do get v. Because you know that this function really is not well defined at the blue point and the yellow point. So this is probably a better and more intuitive way to actually see that v is curl free. I mean, like, you can go back over here to look at this computation, but perhaps my description of v as a gradient of a sum of angles is more enlightening than this algebra here proving that the curl of v is 0. But that's going to be a really important property of our function v. Okay. So what sort of computations can we do knowing that knowing that v is curl free? What are we going to do? So I'm going to add a new page. All right. Oops, I don't have the lines anymore, but that's okay. So what do we get from noting that v is curl free? Notice that v is the sum of v1 plus v2, where you can rewind, actually, where v1 and v2 are over here. And you can actually check that both of those, this is really like this v1, this was the gradient of theta 1, and this v2 is the gradient of theta 2. I'm saying that with like scare quotes because theta 1 and theta 2 are only defined on an open subset of the plane, meaning like there's a strip on which, there's a one-dimensional spot where theta 1 isn't continuous or well-defined, or there's some sort of break in continuity. Okay. But I want to say that v can be decomposed into the sum of these two things, where v1 has singularity at 1, 0, v2 has singularity at -1, 0, and both of these pieces are also individually curl-free. So what I would like to do is I want to make the following computation. So here are my two singular points. That's where the vector field is not defined. And I would like to compute the following. I'm going to let this be, no, I want that to be a unit circle centered at 1, 0. So this is C1, and this is C2. And what I would like to do, okay, I'll label the points, -1, 0, 1, 0, and these are circles of radius 1. I would like to compute the work integrals over C1 and the work integral over C2. Okay, this is what I would like to compute. I'll need to set up some parameterizations, but let me show you how sort of I can use some of this data up here. Okay, I'm going to minimize this, and let's first focus on C1. C1 is a counterclockwise circle which goes about that yellow point 1, 0. So let's focus on C1 v dot t ds. So this is like, I want to say the absolute worst thing you could do is you could say that by Green's theorem, which in my class, we've called that just 2D Stokes. This is incorrect. That the integral over C1 v dot t ds is going to equal the double integral of the curl of v dA over my region R, where this is region R. Okay, and you might be tempted to say that's the double integral of 0 dA, which is 0. That's incorrect. That's incorrect because you can only apply Green's theorem if there is no singularity of the vector field within the solid region, within the full R. The issue is that our circle contains that yellow point. So you can never use one of these fundamental theorems of calculus if you're somehow enclosing a singularity. I know it's just a single point and you're thinking maybe not a lot of significant things happen at a point, but that's very untrue. A lot of significant things can happen even at a point. You can think of there's infinite curl stored at that singularity. This is one way that I've heard people describe it, which I kind of liked. So this is wrong. This is not correct. Instead, let's actually go about and parameterize this thing. So, well, actually, on that note, I know that V1, that V is a sum of V1 plus V2. So I'm going to write as V dot T ds is a sum of V1 plus V2 dot T ds. And I know dot product is, is distributive and integrals are linear. So this is the integral over C1 V1 dot T ds plus C2, so no, C1 V2 dot T ds. Okay, all I've done is I've distributed and have applied linearity. So I'm gonna continue resizing my things. Oops. Well, whatever. Oops. Okay. We're just gonna have to deal with that. Now, if you look at C1, I'll bolden C1 right here. Remember that V1 is the vector field that has the yellow singularity, and V2 is the one that has the blue singularity. So for that reason, I can actually say that this piece, this is 0 because I can apply Stokes' theorem or Green's theorem. Because V2 has no singularities inside C1. The only singularity is the blue singularity, and that's not inside C1. So that thing is 0. That right sum into 0. And so this value really is the integral of V1 dot T ds over C1. So we can actually go ahead and start computing this by hand. The parameterization is R of T is 1 plus cosine of T sine of T, where T is from 0 to 2 pi. Okay. And well, I have no choice. I'm going to have to move to the next page. Okay. And I know that V1 along this curve is negative sine of T all over. If you plug everything in, you actually get 1, comma, cosine of T, essentially plus 1 minus a 1 over 1. I promise the math works out this way. The denominator occurs because a sine squared plus a cosine squared is a 1. And then I have R prime of T is the same thing. So the integral over C1 V1 dot T ds really turns out to be the integral from 0 to 2 pi of sine squared of T plus cosine squared of T dt. You know that's 2 pi. Okay, so we found the answer for, we've discovered what the value of v dot t ds. Notice that I'm using the full v, not v1, not v1 or v2, but the full v over c1 is 2 pi. Okay. And by similar logic, you can compute the integral of v dot t over c2 ds. If you look at the picture, this vector field is you're integrating over this counterclockwise curve. And if you eyeball it, based on the, oh no, sorry, over here, if I do this integration, it looks like for the most part, you're fighting the current. And you actually get a negative circulation integral. So if you believe me, everything is going to work out just as in the C1 case. You'll get the integral of C2 V2 dot T ds, because the V1 piece sort of drops off because you're not enclosing the singularity of V1. And what you'll get is an integral from 0 to 2 pi of negative sine squared minus cosine squared, which is negative 1 dt, which is negative 2 pi. Okay. All right. So this is the information that we learn from actually rolling up our hands, doing some parameterizations, and computing some stuff. It really wasn't that bad. We just had to, use our sine squared plus cosine squared is 1, which is our favorite formula in this class. So I'm going to flip a page, and I promise we're almost done. So the last thing that I want to comment on is, okay, so I'm going to say let C be the following curve, oriented counterclockwise. Okay, so here's my x and y. I'll give you my singular points I'm staying away from, and here was C1, this was C2, and my singular C is something that does all of this. So this is C. This is C. Okay, so the question is, what is the value of the work integral done over C with respect to V? Okay, so an incorrect answer, well, a correct answer is 0. So the answer is 0, but incorrect logic is the following. Green's theorem says the single integral will equal the double integral of the curl dA over the big peanut region. And we know that the double integral of 0 over the region, so that should be 0. Okay, this is incorrect logic. You can't quite say that. Although the answer, the value of this integral truly is 0. And let me explain why, and then we'll be done. So I'm just minimizing this. Okay. We will use Stokes, and we will use Green's theorem, but we'll use it in a slightly different way. So instead, I'm going to draw a region, which is, there's C. Here, that's C1, and that is C2. And I'm going to color in red what my region R looks like. Okay, so where I've shaded in red, I'm going to call that R for red. And I want to look at the boundary of R. So I'm also going to look at the boundary of R, and I know it's going to be plus or minus C, plus or minus C1, plus or minus C2. So to figure out if it's plus or minus on each of these summands, I need to see if the orientation of the curves is agreeing or disagreeing with what R has to offer. So if I do a counterclockwise spin, I see that I'm agreeing with C, but disagreeing with C1. And if I do the same thing over here, I see that I am disagreeing with C2. this tells me that the boundary of R is C minus C1 minus C2. Furthermore, note that V has no singularities inside R. This allows us to use Green's theorem. Green's theorem, or to the 2D Stokes theorem, always works if your solid region stays neatly away from the singular points. And we see that's definitely happening, or R is not overlapping with the two bad, like scare quotes, bad points. Okay, so in fact, you can actually use this. You can say that the double integral over R of curl of V dA, we know that to be the double integral of 0 over the region R, that's for sure, is going to equal, I'm going to use this fact over here, I'll highlight that in purple, is going to equal a single integral of V dot T over C ds minus a single integral over C1 and a single integral over C2 V dot T ds. Okay. Now we have almost everything we need. Because what? We have this thing, which we're trying to compute. This thing we computed was, what did we say? This was 2 pi. And this thing we said was negative 2 pi from the previous over here. I'm using this fact and I'm using this fact. Finally, to put everything together, I'll highlight what I'm looking for. That purple, the integral C V dot T ds is equal to, I push those over to the other side, 0 plus 2 pi minus 2 pi. If I clean that up, that gives me 0. So indeed, the value of this work integral is 0. It's not for this reason right there. It's for this reason right here. So there's a lot to learn from this example, and I hope this was illustrative in some way.